Hello and welcome to the introduction of a software package we have prepared to analyze stochastic data, in particular time series of load processes measured in a simulation, in our case mostly from wind tunnel testing. And this software package should help to understand the characteristics in the load process, but also should provide a tool to determine characteristic parameters of the loading we will later use in the design of the structures. This package contains several scripts. It's all written in Matlab. So, and the first script is a time history analysis, THA, which allows to look into the time history to see how it actually evolves over time and provides some tools to reveal the statistical characteristics of the time history. Secondly, a script which looks at the correlation of two time series, and this is often helpful understanding how the load at two different points of the structure is correlated with each other, which means how simultaneous is the load increasing or decreasing, and with that we do get an image or an idea about how large is the area which is at the same time loaded with a very high load and so on. The third is a script which visualizes the interaction, or let's say the combination of two probability densities, the joint probability density, so to say. So, and this is the platform, this is the basis to understand how to calculate an overload risk of a certain system, which depends on, let's say, two variables. In one case it can be the resistance of a structure, and on the other side it can be the load of the structure. And if these two elements do play with each other and combined with each other, the resulting joint probability is used to calculate the overall exceeding of a specific load level.
To say it in short, the package contains three Matlab scripts. One is dealing with the analysis of a single time history. The second looks at the correlation between two time series. And the third allows calculating and displaying the joint probability between two stochastic variables. All three scripts are documented in a user's manual that also provides additional information on the routines used in the scripts.
So, but first have a look at the time history analysis.
In this connection, we can discuss what actually is a time history. Well, a time history is a data set which contains the record of a phenomenon we have observed either in nature or in a simulation. The data set which is making the time history allows us now to look at the variation over time, and we can study in detail the characteristics with which the phenomenon is changing and varying over time. For example, in this variation or in this time history, we can identify a minimum and a maximum value, which later becomes relevant if we talk about extreme loads or relevant or characteristic loads for structural design, if this would be a load time history. So furthermore, we can say that the values, the individual data points within this time history do vary around a common mean value. So, but if we now talk about an observation in time and a set of data points, so we have to remember that the time record of a phenomenon in time is in principle, or that what we understand under it, a continuous process. So which means it doesn't contain any holes, it is a continuous development of a load, wind speed or whatever in time. So, but the measuring process now converts this continuous process into the data set we are working with. And that means that the continuous line we actually have in mind when we are looking at the time history consists of individual data points. And the quality of the measurement of the record depends on how fast have we sampled the phenomenon in our observation, that all the features which are contained in nature or in the simulation are represented by the data set we are now using for our analysis. This is, if we now run the script of time history analysis, the output on the screen. So we do have, first of all, a window which describes, or where we can look actually at the development of the time history. Then secondly, we have a window which shows us the density of the data points. So in which fashion are the individual points we have now recorded arranged around the mean value. Third, we have a window which is reflecting the spectral density, the energy spectrum in our time history. And then we have a window, if we divide our time record into into a shorter sub-series, we have a graph which shows us the mean value and the standard deviation of the individual time of the individual sub-series. And last but not least, we have the window, the command window, in which the overall information of the used time history is printed. For example, how many data points we have, how long is the time history, and so on and so forth. So let's focus on the time history as such. There are all different types of data sets possible which we can work with, but if we just look at the simplest case, so then we have a data set consisting of two columns. The first one is the time axis, preferably given in seconds or whatever is suitable. And secondly, the second column contains the value of the variable of the phenomenon which we are going to investigate. So the sequence of reading data from an external file is given here as an example. So, and it does start with opening the file. So these are standard Matlab routines, and it reads a two-column file of infinite length, closes it and puts it on the work vector series. So further on, we need to assign now the time axis to the vector tx, and x0 is the time history we are looking at. If we would have read a data file with several columns, if we have several signals, several data sets to look at, so then we can decide which one is now assigned to the x0 to the x0 vector, which is now the time history which is going to be analyzed. The next thing we need is the step width of the time steps, dt, which is calculated from the time history, and from that we calculate also the sample frequency, which is just the inverse of the time step, which is later used in the analysis.
What we have seen here is that the continuous time series, what actually is happening in nature, is in the analysis, so that where we are using it represented by individual data points. And this is because of the sampling of the signal. It is due to the processing of translating an analog signal into something digital, giving it numbers of the amplitude in the instant of time. So which means that we have a collection of individual data points. So, and the difference, for example, to any other collection of individual data points is that in our case of a time history, the specific sequence of these points over time is actually the main property of that, what makes a time history. How fast are these individual values of the time history changing, or whether they do change over a longer period of time. This is very, very unique to a time history, and this is very important if we do talk about loading and if we do talk about the dynamic response of our structure. The next thing we are now looking at is how close the data points are to each other. This reveals let's say the bandwidth of the load process. So whether we do have a large change within our measured time series of the loading, or whether the data points are very close to each other, which means that we could expect that the load is quite stable. If it would be constant, so we would have no variation at all, it would be revealed in one value only. But since we usually always deal with a quantity with a loading or response which does vary in time, so we do have a certain width of the response, a certain range of the data points. So let's see how we can describe the characteristic of this scatter of the data points within our measured time series.
So the next thing we're looking at is the density of our data points within the measured time history. So if we now use a data set and we would like to know how broad or in which fashion the data points do spread over the measured range, so we can apply a set of bins which we use to count the number of data points which do fall within the individual bin. So if we do that, we get an image about in which fashion, in which way now these data points are arranged over the entire data range, which means between the maximum and minimum value we have obtained within the observation time. So this count can now be normalized by the number of the total data points, and with that we do get the relative frequency of the data points. So this relative frequency is in principle a reflection of that what we call the density function of the data points of the sampled space. So, and by that and by nature, the area underneath this density function is 1, because this is 100% of all the measured data points, and they are distributed in this particular way around the mean value, or let's say again between the maximum and minimum value obtained. So in the script where we define all the main parameters for the analysis, the number of bins is given by the variable nbin, and you can play with it to give more or less bins. This depends on how much data points you have, but of course also how much they actually do vary over time. So talking about the density functions, there are from literature different types of density functions. There is, for example, the normal distribution with the density and the distribution function. So then we do have the Weibull distribution, for example, for the daily mean wind speeds, and we do have a Gumbel distribution, which usually is used to describe the characteristics of extremes, for example, extreme storms or also extreme responses and so on and so forth. There are many other distribution functions in literature, but these are those we are in wind engineering using the most, and also those we are going to apply in the different exercises in this course. So again, what are the characteristics if we now look at a density distribution? So one thing we can say, well, there is a value which cuts the distribution into equal sized halves. This is the median value. So secondly, we have the modal value, which marks the top of the distribution curve and is by that the most frequent value. Remember, from the histogram. So this peak actually indicates that we have most counts of this value within our measured time history. So, and then third, we have the mean value, so the statistical mean value of all data points, and all these three values not necessarily have to be one and the same, especially if the distribution is not symmetrically distributed. In case of a normal distribution, which is by nature or by definition symmetric, all three values are identical. But if we do have, as I said, a unsymmetric distribution, they are all different and mark different, let's say, properties in the distribution. So how much now the variation of the data points are around the mean value can be expressed by that what we call the moments of the distribution function. So if we look a little bit closer of what this means, so we have, for example, the first moment of the distribution function, and this is the sum of all data points divided by the number of data points, which is just the mean value of the distribution. This is the first moment. Secondly, we can look at the difference of the individual data point, and this is, if I mark here at this point, this is the difference of the individual data point to that what we now consider as the mean value. Or here, if we have this in a summation form, yes, this is the individual data point and this is the mean value we have calculated before. So, and this difference is in principle nothing else but the variation of the data sets or of the data points from the mean value. Summing them up and dividing them again by the number of data points -1 gives us the variation or the variance of the of our data set. Third, we can use again the variation of the individual data points to the mean value, but we have now power 3 of these differences, and this allows us to estimate the skewness of the distribution of the density shape. If this value would be negative, we would have a distribution which leans to the left side in our graph. If the value here, the skewness, becomes positive, the curve of our density function leans towards the right side of our graph. And finally, if we use again, or if we apply the fourth power to the differences from our data points to the mean value, so here at the bottom, so then we can get a measure of the kurtosis of the axis, in principle pointing how pointy, how sharp the distribution function actually is. So how much this actually means and how strong this is manifesting in the graph. So the best way of finding that out is just to take some data points, run it through, calculate the data, and then you get a good feeling of what these different moments or the values for the different moments actually mean and how you can use them in the analysis. So far, we have looked at the individual data points and how they are distributed over the observed range between the minimum and maximum value. Now we want to know how the data points are distributed over time, because the way in which they vary reveals information on the inner structure of the phenomenon and allows us to think about how this variation may affect us or our structures. This information we get from the spectral density function or power spectrum. So what is behind the idea of a spectral density or a power spectrum? Well, the basic concept is that we say that any stochastic process, in our case the measured time series, can be described by a suitable combination of fundamental harmonic functions. If we look here at the graph, we have at the top here our time series, and that is described here, for example, by the variance, and we have the mean value and so on and so forth. So, but this time series can now be decomposed into fundamental harmonic functions. Here down below we have a set of different functions, each of which has its own frequency, it has a specific amplitude, and it has a phase angle, which means the phase angle determines the time shift or the location of the fundamental wave on the time axis. In other words, the reconstruction builds on combining harmonic functions with different frequency, amplitude, and phase angle. The fast Fourier transform uses this concept to decompose a stochastic variable, or more precise, the time series of a stochastic variable, into fundamental components, meaning into a set of fundamental harmonic functions. If we now look at a single fundamental function, its contribution is, apart from the time shift, apart from the phase angle, defined by its period or frequency and its amplitude. So the entire reconstruction can be defined by a function showing the amplitude for each frequency contribution. And this function, this relation, is actually given here in an amplitude spectrum where we have the amplitude given for each individual frequency contribution. This amplitude spectrum can be translated into the power spectrum, into the spectral density of our time process. If now the entire variation around the mean value is constructed through combining waves of different frequency, the power spectrum is an image of how the variation is distributed over frequency. Well, that means if we integrate the spectrum, the area underneath gives the variance of the time process we are looking at. Scaling the spectral ordinates with the variance normalizes the area underneath the spectral curve. So how does that relate to phenomenon we are dealing with in wind engineering?
Well, the decomposition of a stochastic signal into fundamental harmonic waves is the basic principle for any Fourier transform. But if we relate this to something more physical in wind engineering and with respect to our loading, so we can have a look again at how we do describe the wind, the turbulence in the wind, and how this turbulence, this irregularity in the wind speed does affect our structure. So let's have a look again here on our wind field, so which we have over a certain height and over a certain distance. So, and the turbulence in the wind we describe as vorticity, as rotation of smaller and larger scale. And if we say that we have here down at the ground, we have our terrain roughness, we have here our buildings, we have towers, we may have some hills behind it, we may have trees, forests. So this is the roughness of the surface of the earth in all its variety possible. So, but this induces, apart from other atmospheric effects, but if we keep it simple, this induces some rotation in the flow. It is irregular. It does go up and down. It goes over the hills. It separates and it creates structures which we do feel or we experience now if we are exposed to the wind as gusts, as irregularity, as the turbulence in the flow. So and if we now say that, okay, these structural elements do assume somehow a shape or a volume which is a little bit football-like shape, they are elongated compared to their width and their height. So and the higher we do get, we have larger of these parts. Of course, they do interact with each other, so they are of larger and smaller scale. It's a conglomerate of different sizes of eddies. But if we now look here at our wind velocity profile, so if we say, look, this is here in principle what we do get in average. Yeah, so this is the velocity. profile. So all these elements do create here at an instant, in second, in time, a variety of our mean wind speed profile. So, and this leads to that effectively, if we take a snapshot in time, our instantaneous velocity distribution may look like something like this. So this is in principle the engulfing, it's the outer part of that what the turbulence eddies do to the motion of the wind. So as well as we have said that we have now a stochastic process and we zoom into the composition or the contributions of fundamental harmonic functions, we could say, well, the stochastics or the stochastic character of the wind is a result of other components, meaning of these turbulences. We could say that if we zoom into one of these elements, so this is a vortex. So, and this is a vortex of a certain length, and it's traveling with a certain speed. So even though it may rotate, it spins, so there are all different type of motions it can assume. So it rotates, it spins, but nonetheless, it travels in principle with the same speed as we have here for our mean velocity. If this here's the profile, so this here is the mean travel speed we have for that particular level of the flow. The higher levels do move faster, the closer we are to the surface of the Earth, the slower they move. But this here is traveling now here with our average speed here at this particular height. And this means if we now experience this vortex, if we measure it, for example, or if it hits a mast, so this gives a certain length of impulse, a certain length of the pulse of loading. And this pulse of loading, we could say, okay, if this is now here our measuring point, where this vortex is now passing, and we have here our measuring instrument, we say at the time of impact, if this is now traveling further and it starts hitting here our structure, so we do get a start of a signal, then it passes, so which means we have some kind of signal, and I draw it here now as a sinusoidal signal just to have a period, a complete set of a isolated individual signal of an isolated individual vortex. So this means that this time, so this here is still the time, relates to the length of our vortex and the velocity it travels with, so which means that this signal has a specific frequency. So with that, we are again back to that what we discussed before, so that our wind can be interpreted as a combination of different individual harmonic signals, meaning it is, if we talk about the turbulent wind or the turbulent structure in the wind, it is a composition of different sized vortices which do act together. They are not isolated as such, and over time they also decompose into smaller structures. But nonetheless, if we look at a specific moment in time, and if the entire flow is in equilibrium, which means we do create turbulence, we transport it, and it dissipates, so then we have a certain combination. Let's say it's a construction plan, it's the DNA of the turbulent flow, and this is also a way of looking at the energy spectrum of the flow. And this is the input to estimate if I have a structure with a certain eigenfrequency moving in a certain specific eigenmode, in a certain specific motion, so that this energy, this contribution at the eigenfrequency of the structure will create a certain resonant effect. So from there on, we have to think about how do we cope with this resonant effect in dynamic responses, and how much damping we do need to dissipate the energy so that we do not have motions in our structure larger than that we would like to have. So this is a different, or it's an alternative to the interpretation of just decomposing a stochastic process completely abstract into basic waves. So this is the physical interpretation of the wind and how we do apply the energy spectrum in this way. So after we have now looked at how the time series does look like over time, we have now looked at how the values are distributed to each other. We have the density of our data points. Third, we have now looked at the energy spectrum. So how is the variation inside our time history distributed over frequency, which frequency is contributing with which intensity to the overall load process. But now we go into the next step where we do start collecting extreme values. I said at the start that this software package has been made to analyze time histories viewed as load time histories, and it is used to determine, to estimate characteristic loads. So, and if we do talk about loading on our structures, we do talk about extremes. So it's not necessarily the mean value of the load which is relevant for our design. Of course, it characterizes so where the overall load level is, but it's not actually that what is used for the design. For the design, we are interested in the maximum loadings. Those are extreme, and that are, of course, by nature more rare events, but these are those which do load our structure to the maximum. So, and for that we have to design and we have to take care of that the resistance, that the strength of our structure can withstand those extreme loadings. So how do we collect these extreme loads?
One of our main tasks in wind engineering is the estimation of the characteristic loading value which we use for our structural design. So if we now have the information in our data set, in the recording of a load time history, for example, we need now to collect a suitable set of extreme values which we can now use in an analysis to come up with a value for the characteristic loading. One standard way or common way of doing it is to subdivide our time history into subseries. We now consider each subseries as an individual loading event within which the loading is of course varying, but we can use these series now to collect data sets. The length of each data set should be sufficiently long. It should be long enough to represent the characteristics of the overall loading. So not that we have loading events which are significantly lower than all the others, which then would not be suitable for collecting peak values for the characteristic value. And this again is the idea of the ergodicity, so that all the subseries should be in their characteristics equal to each other, but of course in their particular making, in their particular variation, they do vary and are different from each other. Anyway, so now we have the different time series and we now assume that they are of suitable length. So we can identify within each individual time series a individual peak. So these values are now collected in a sample population, in a sample space, which is used for further analysis of the extreme values. So, and this is what you get when you run the script. So, first of all, it reads, of course, all the data points in. Then it gives you the window with the time series. Then the next one is the window with the histogram or the probability density. Then we have the spectral density and the window with the statistical data from the defined subseries. So what happens if we define now several subseries apart from one? So for example, we give here 20 subseries, save and run. So then the program marks on the time series the position of all the sub-events, and the fourth window gives you now for each sub-event the standard deviation, the RMS value, and the corresponding mean value. And that compared to, and this is what the stapled line is, to the overall mean value of the entire time series. So we can now access the data from the subseries. For example, if we go to the command window and give smax with capital S max, so then it gives out all the maximum values from the subseries, as mean would give all the average values, or we can as well give the entire set of S mean, S RMS for the standard deviation, next the S min for all minimum values, and S max for all maximum values. So, and if we give that back, we get the full matrix of all the statistical parameter from the subseries. And these values can now be taken, can be copied from the screen into the further analysis of, for example, extreme value analysis and so on.
Okay, let's come to the second script of the software package for the time history correlation. So I said at the beginning that the correlation between two time series gives us a lot of information about how the loading is distributed over a structure. If we, for example, take here a high-rise building where we do have measured at several points the loading, which means from each of these points we do get an individual time series. So it is very important to see whether overall these points, so here we do come to the top of the building, so whether the loading is completely correlated here at this point, or does it change when we approaching the corner, so the flow is accelerating around. So where does the load maybe decrease or even increase compared to the neighboring part? So this is what the time history correlation is looking at. So let's see how this works.
In the next script, we are looking at the correlation between two time histories. For example, the correlation is relevant if we look at a suspension bridge or a long bridge, and we need the information whether the loading, and especially the variation of the loading on the bridge deck or pylon or whatever, is the same or is similar to each other over a certain distance. And by that we could compare the recorded time histories of the, let's say, the approaching wind at different points. We could say that the midspan of our bridge deck is the reference point, and the second point is varying in distance along the bridge deck. And if we look at each individual comparison, we could get an idea about at which point now the loading process starts getting decorrelated, which means it varies in its own fashion compared to our reference point, and by that the load would also be disconnected. It would not act in the same way, or at least not at the same time in the same way as our reference point. But anyway, so let's have a look of how this correlation can be used and can be analyzed. So we do now have here two time histories measured at a certain distance. So, and we would like to get an image about what the correlation actually does look like. So we look now at a specific point in time and say at this particular point, both time histories do have a certain value. In the first and the second one, we have an ordinate, and these ordinates can now be transferred to a graph where we have on the x-axis the scale for the first time history, and we have on the vertical axis, for example, the value axis for the second time history. So if we now use these two ordinate values as coordinates, so then we can say that the correlation between these two data sets at that particular point resolves or leads to a particular position of that let's say, combination on this graph. This graphic representation can now be repeated for all data points of both time histories and leads to a picture of how these data points do follow and how they are correlated to each other. And this is what the script is about. We have here the two time histories, and in the upper right corner we have the graph where all the data points are compared to each other at the same instant of time. This is the input sequence from the script. It is very similar to that what we had from the time history analysis. Only difference here is that for presentation purpose of the graph, we have generated ourselves the values for the time axis calculated from a given sample frequency. But this is not really necessary. We can as well just use the data points as they are. XA and XB are the two vectors for the first and the second time series, and depending on how your data set is designed, in this case we have several signals within one external file, so you can assign whatever you read to the two vectors. Main point is that XA and XB contain two series of the same length. Let's have a short look at the relation between the two time histories and the correlation coefficient we can calculate from the two time histories. The correlation coefficient, here off to the right, is calculated as the ratio of the covariance between the two time histories and the product of the standard deviation of each individual time history. So the correlation coefficient now indicates how much the two variations in the one and the other time history are related to each other. One would mean, as in this case, that they are completely following each other, they are almost, or that they are identical. If the correlation coefficient indicates -1, still it means that they're following very synchronized over time, but the ordinate of the individual time series is opposite to each other. By that we have in principle a full correlation where we just have opposite sides. Between -1 and 1 we have now all different possibilities of how the two time histories can be related to each other, and this is of course depending on the frequency of the one on the other, and whether there is a time shift between the two time histories. So if we now go back and apply this graphical presentation of the correlation or of the relation between the two time histories, two identical time histories would in principle make on this correlation graph a straight line. Slightly changing the phase angle, or having a small time shift of the one time history to the other, already changes this straight line into an elliptical representation of the data points. These graphs give us additional information on the relation between the two time histories. The correlation coefficient we have calculated in principle only indicates the noisiness of the cloud graph and the direction of the point cloud. If the correlation is 1, the noisiness is reduced, or the graph is reduced to a straight line. And if the correlation is positive, we have a positive inclination of the graph. And if the correlation becomes negative, we also have a negative inclination of the graph. The inclination of the graph gives us an idea about the relation between the amplitudes of the two time histories.
So now we do come to the third script in the software package which works with the joint probability density of two variables. So now in the first, or with the first software package, we have to look at the time series of a certain loading, and we could calculate, or we could estimate the density function of that particular load process. In the same way, you could do a distribution density of, let's say, material strength or robustness of some structural members. So, and these two parts stand now opposite to each other, where the loading is imposing the stress and the material has to bear the stress. The structure has to distribute the loading, and the members have to be able to cope with the induced stress. So these are two, let's say, stochastic variables, and of course both are, even also the material, are stochastically so distributed, so which means if you measure the elasticity modulo of one element, you get slightly a different number in the next test, and so on and so forth. So which means both are probabilistic or probability variables, so to say. This program visualizes how these two independent variables interact with each other and how to use the information on each individual variable, load and resistance, to calculate an overload risk or whatever one might be interested in when two independent variables interact with each other. So let's see how this works.
We come now to the third script in the software package, which is calculating and presenting the joint probability of two stochastic variables. Here in this example, one stochastic variable can be the resistance of a structure determined by the property of the material. On the other side, we have the loading as a stochastic variable, which is inducing stress in our structure. For design purpose, we would like to have the resistance in our structure much larger than the stress which is created by the loading. The further these two are away from each other, the higher is, so to say, the safety in our structure. So if we now use this information and assumed we have made an investigation which gives us the probability density of the material, meaning the resistance, and we have made an analysis of the loading process, which gives us the density function of the loading, which we can convert into the process of stress in our structure, we would like to ensure a certain level of safety. So how do we do that? If we can assume that these two stochastic variables are independent of each other, we can calculate the joint probability between these two variables, and we can use that joint probability to define a safety level we find acceptable for the design of our structure. So how can we calculate the joint probability of these two stochastic variables? Well, we said that each variable is now described by the mean value, by the dispersion, and by the probability distribution function, and so on and so forth. Furthermore, we said that both are independent of each other. Combining the probability of a specific stress value with the probability of a specific resistance value gives us the joint probability. If we apply that to all values in the stress and to all values in the resistance, we do get the joint probability. So, and this is in the Cartesian coordinate system reflected by this hill-like shape. So we would like to have, of course, the values of the resistance being much larger than those induced by the stress. So, and this line here is now cutting the joint probability where the stress becomes larger than that what the resistance can accept. So if we look on top of this graph, so this area, this volume underneath the joint probability on the side where the stress is larger than the resistance, we get an overload, or we get an overload risk, to be more precise, and this is defining the safety level in our structure. So which means the larger the center of the joint probability is away from that, let's say, decision line for overloading, the more safe our structure gets. So, and this is what the semi-probabilistic design of the Eurocode is regulating. It tries to maintain a certain safety level, disregarding which type of material we have, which means of resistance, and which type of loading we have. But for that we need to know the characteristic of our loading, and for that we need to define the characteristic value which we are using in the structural design to maintain exactly that level of safety. So if we go back and use the graph from the correlation script, so then this joint probability is in principle the histogram above the dot cloud we have in our correlation graph. And this is how it's done in the script. So we assume we have made some pre-analysis and we do know the density function, for example, of the wind loading, and we know the density function, in this case it's now for air temperature. So again we assume a sufficient independence of both, and we do calculate the joint probability by combining the probability of each contribution from wind with temperature with each other, and that can be plotted as a three-dimensional graph. So this can now be used, of course, for visualizing how these two are actually together, how this joint probability actually does look like. But if we now introduce some decision lines, and this is now here the top view, if we, for example, say that we would like to have the probability of cases, let's say, where the wind speed is above 6 meters per second and the air temperature is below 2 degrees Celsius. So this is the case we are interested in as an example. So we can just define this decision function and integrate up the joint probability to come up with the risk, or with the probability of these cases occurring. So we can now define all different type of decision functions. This depends on the application, whether you're looking at structural safety, or you're looking at wind comfort, or some other environmental issues. The script allows you to calculate the joint probability, to visualize the joint probability, and to have a graphical control about the joint probability and the decision functions you are going to introduce for the investigation of your particular question.
So I have now gone through all the scripts within the software package. I hope you get an idea and a feeling about what the purpose is, how the different software packages, how the scripts do work, what you do get out, and what you can use it for. So the next thing is just open them, start them, try them out, vary parameters, look at the results, play with them, and I think this should give you a comprehensive overview and introduction, a feeling for how to analyze stochastic signals, stochastic processes, and use them in structural design.